Thanks. So we'll continue our discussion on redistribution mechanisms. So let me just remind you the model once more. So there are n agents. There's a single divisible object. So think of it as a firm with lots of shares. And this object needs to be allocated to the n agents. Each agent has a value per unit value Vi for the object and gets value Vi Qi if Qi part of the object is given. Values are independently and identically drawn from 0 beta with distribution capital F and PDF small f. Okay, so all the agents are symmetric ex ante informationally. What is different from this model to the Myerson's model is that each agent owns a share Ri of the object with sum of the Ri's equal to 1. Okay. And this is what I will call it the share vector or the property right structure, and I'll call it with different names, but it will become critical for defining the participation constraint. Okay, so some of the partnerships that I wanted you to keep in mind is that when all the agents except one of the agents has Ri equal to 1 and others have Rj equal to 0 for all j not equal to I. So all the property rights is held by one agent. In that case, that agent would be equivalent to a seller, right, who owns the object, and the other n-1 agents are buyers. Okay. So that would be an interesting model that we will look at. The other interesting model is when the partnership structure is completely symmetric, which is what we call the equal partnership model, where everybody has equal property rights over the object. Okay, and then slightly less interesting, but we'll come to it, is the property right structure where there is only one buyer, that is one of the agents has 0 property rights and everybody else has some property rights. And so in this case, I have just taken it to be 1 over n-1. Okay, so let's keep these share vectors in mind. So the result will have corollaries for each of these 3 particular property right structures. And so we were talking about mechanisms in this setting, Q and T. And Q is the allocation rule, T is the transfer rule. The only thing is like Ti is supposed to be interpreted as the amount received by agent I. Okay, that's what you should keep in mind. And we'll always assume that these things are feasible. So in the sense that sum of QIV is less than equal to 1 and transfers are budget balance. So sum of TIV is equal to 0. As you will see later that this is not really required. In fact, if sum of TIV is less than equal to 0, then also everything that I'm saying will go through. But this is just makes life a little easier in terms of calculations and so on. That's all. So we defined the incentive and participation constraints last time. It's Bayesian incentive compatibility and interim individual rationality, where here basically this small Qi is the interim allocation probability and small Ti is the interim payments. So this basically says that the interim payoff is greater than equal to RIVI, where Ri is the current share of agent I in the partnership, okay, or over the object. Okay. So we defined what we mean by dissolving a partnership efficiently. So a partnership, which is a share vector, can be dissolved efficiently if there exists feasible, meaning that the sum of QIV is less than equal to 1 and budget balance holds, efficient, Bayesian incentive compatible, and interim individually rational mechanism for this partnership. Okay, so that's what we mean by dissolving a partnership. So this is a new slide that I have put in. This was not there last time. So I want to, maybe some of you already realize it, but I want to still stress the fact that there is a reason we are putting this budget balance condition in this. And that comes from the, the motivation for that is that we want to redistribute as much surplus as possible. And so that's what I'm going to rigorously show in this slide, that budget balance allows you to, maximally share the surplus. Okay. So to see that, take any profile V and notice that the sum of utilities of agents in any mechanism Qt can be written as this. So, so this is the sum of utilities of the agents. Well, what is the utility of agent I in this mechanism at valuation profile V? Well, he gets VI QIV, so that's his expected value, or this is the share he's getting from the mechanism times his value VI. Plus he gets a transfer of TIV. So this is his utility and summed across all the agents. Now notice that if sum of TIV is less than equal to 0, that is the mechanism can only receive, the designer can only receive transfers in aggregate. It can never subsidize the agents. Then this expression is less than equal to this, right? Because sum of TIV is less than equal to 0. So in that case, we can say that the sum of utilities is less than equal to sum of these values. Okay. Now this term is less than equal to max VI, right? Because because all these QIs are between 0 and 1. So this has to be less than equal to max of VI. So what we have just shown is that if I take any mechanism Qt and the sum of TIV is less than equal to 0 at every valuation profile, then the sum of utilities is upper bounded by max of VI. You can't get a total sum of utilities more than maximum of VI. Okay. But we can achieve this upper bound by a particular choice of Q and T. Okay, by choosing Q to be the efficient mechanism and T to be budget balance. Okay, so why is that? Well, if T is budget balance, then this inequality becomes an equality. And if Q is efficient, then this inequality also becomes an equality. All of you agree with that?
Yes, sir.
Yeah. So if Q is efficient and T is budget balance, all these inequalities become equality. Okay. So in some sense, by choosing Q to be efficient and T to be budget balance, we maximize the sum of payoffs that we can give to the agents. And that's the reason, I mean, any mechanism which tries to maximize the payoffs that it wants to give to the agents, okay, must have efficiency and budget balance. Okay. Okay, so this is inside the class of mechanisms which satisfy this property. And of course, if this property is not satisfied, I can always maximize the sum of payoffs by giving the agents a lot of money, right? If I have a lot of money, the designer has a lot of money, it can always pump in money and maximize the sum of payoffs. But here we are working under the constraint that the designer has nothing to offer to the agents. It can only redistribute the surplus the agents generate. And basically the maximum the agents can generate is VI. And this basically, if you want to maximize your payoffs, you better choose a mechanism which is efficient and budget balanced. Okay. So the question, so the choice of efficiency and budget balance is, comes from the motivation that we want to maximize the sum of payoffs of the agent. So the question is, can we achieve this efficiency and budget balance in the presence of incentive and participation constraints? So that's basically the question. Okay. If we did not have these two constraints, then we can, basically we know what everybody's payoff is. We can just, we know everybody's type, what it is, and basically take max of VI from the highest guy and distribute it whatever we want. But we are not supposed to be doing that, because then we won't satisfy incentive and participation constraint. So that's what the key question is. That's why the question is interesting, that can we achieve this efficiency and budget balance and hence maximize the payoffs to the agents by maintaining incentive compatibility and individual rationality. Okay, so I hope that part is clear now, that why we are interested in this question in the first place. Any questions? Okay. So the tools that we are going to use for analyzing whether efficiency and budget balance is compatible with incentive compatibility and individual rationality is the Myerson toolkit. So we know what the characterization of incentive compatibility is. And so that's what this is, that the interim allocation rule is non-decreasing, and this TI satisfies some revenue equivalence formula. So we start from there. And then we observe that because we are using efficient allocation rule, the interim allocation probabilities can be defined very particularly. So, okay. So in particular, the interim allocation probability of an agent I, which has a value VI, is this f of VI to the power n minus 1. Okay. So which we denote as capital GVI. And we observe that G itself is a probability distribution. It is the probability distribution of max of n minus 1 independently drawn random variables. And so G is a probability distribution, and small g is its PDF. And we are going to use this repeatedly. This capital G and small g will appear at many places in many of the formulas that we are going to derive. And so last time what we observed is that if I take any efficient and Bayesian incentive compatible mechanism, QE and T, then the marginal payoff of an agent is maximized at this type V star I, where V star I is just the type at which the interim allocation probability is equal to its property right, or its share, Ri. Okay, so G of V star I, remember, is the interim allocation probability of a type with value V star I, and this says that this G of V star I is basically equal to Ri. So that's how I'm defining V star I. V star I is defined like this. And so what here we are showing is that the marginal payoff is maximized at this V star I. Okay. Did I say maximize? It should be minimized. So the minimum marginal payoff occurs at V star I. Okay. So that means that every other type would have larger marginal payoff. So when I say marginal payoff, it is the payoff from the mechanism minus RIVI, which is the payoff that the agents are already getting. Okay. And this is just the proof of this is just a first order condition. Basically, U is a convex function, and so U minus Ri, so this UIVI minus RIVI is also a convex function. And so basically you can minimize it by taking the first order condition. Okay, so that and the first order condition will just give you this. Okay, so that's what we had done yesterday. I mean, the last lecture. So this is the, and this is also, I think we had done last time, that IIR is equivalent to requiring that TI V star I is greater than equal to 0, right? Because, so IIR would basically mean that this is greater than equal to 0, but that can be ensured now by just requiring this to be greater than equal to 0. And this term is basically if you expand ui b star I, okay, so this is this term, but this is the same as this. So these two cancel out. And so we are left with this. So basically requiring this to be non-negative is equivalent to requiring ti b star I to be non-negative. That's what this is, okay? So in the Myerson's world, because there was no property rights, the IIR was equivalent to saying that TI 0 is greater than equal to 0. But here, because of property rights, the it's the sufficient condition, necessary and sufficient condition is modified to be TI V star I is greater than equal to 0. Okay, any questions on this so far? Okay. So now we move on to the characterization. So the Crampton-Gibbons-Klemperer's main result is a complete description of all the partnerships that can be dissolved efficiently. So they say that a partnership R can be dissolved efficiently if and only if this condition holds. And this condition depends on R's in a in a indirect way, so to say. Basically, it enters Ri enters this equation through V star I. Remember, V star I is defined as G of V star I is equal to Ri. So the limits of this integral basically has V star I, and so that's how this inequality depends on Ri's, and the integrals are over these distributions F and G, and so and I'll show you how why this condition is necessary and why it is sufficient. Okay, we'll see that. So one thing to note is that it's a complicated condition involving F, G, and Ri's and so on, but it's a characterization. If you feed it to a computer program, you can basically ask any share vector and see if it satisfies that inequality. It's a single inequality, and you can basically find out. Okay. More importantly, later in the lecture, I'll show you many interesting corollaries which we can get by using this condition. Okay, so that's where the power of this characterization will come into force. Okay, so let me do the necessary direction first, which is the easier direction, that if a partnership can be dissolved efficiently, then this condition must hold. Okay, let's try to prove that. Okay, so suppose QET is an efficient BIC and interim individually rational feasible mechanism for this partnership R. Then we know that because it's a budget balance mechanism, then basically total payment collected at every type profile is equal to 0. So the expected payment collected from all the agents across all the profiles must also be equal to 0. So that's what this is doing. This is the expected payment of agent I in the mechanism. This is the sum of expected payments of all the agents in the mechanism. Just rewriting this will just give you what is the expected payment collected from this mechanism. But because it is budget balance, this term is 0. So this is equal to 0. So this is the first observation, that any budget balance mechanism will have this property that the expected payment collected from the mechanism must be equal to 0. Okay. Now we are going to use the Bayesian incentive compatibility, characterization, which basically said that the interim payment at any type VI can be written as the interim payment at the lowest type. Well, not the lowest type in this case, but it's the interim payment at the type where you get the lowest possible marginal payoff, which is V star I, plus minus some terms which will depend on basically the allocation probabilities which are given by these G functions. So G functions are, remember, I have already told you that the capital G is like the interim allocation probability here, because QEV is equal to GIV. Okay, so that's why this is written in the G terminology. Okay, so this equation follows from Bayesian incentive compatibility, that revenue equivalence formula. So what I have done here is that simple algebraic manipulation. This one, this term after the TI V star I can be written compactly by this particular integral. So if you integrate this term by parts, you'll exactly get this. Okay. So you integrate this by parts, you exactly get this. Okay. So that's what this is. So Ti V star I minus this term. Okay. Now the last step is where I'm using interim individual rationality. Remember the characterization of interim individual rationality. Ti V star I has to be greater than or equal to 0. That's what I'm using here. So Ti V star I is greater than or equal to 0. So this term, these two terms is greater than or equal to this term. So here I have changed the limits of the interchange, the limits of the integral to make this minus a plus. Okay. So what this is saying is that bottom line is that transfers are lower bounded by this expression due to Bayesian incentive compatibility and IIR. So you can use Bayesian incentive compatibility and IIR to bound the interim transfer of every agent at a particular time.
And also efficiency, BICIR and efficiency.
Of course, we are using efficiency in the first place itself, because this GVI is equal to QEIVI, right? So efficient allocation rules interim probabilities. Okay, so we are using efficiency here. So we have used budget balance here, and we have used everything else here.
Sir, for some types, this bound is positive, but it can be negative as well. So how to interpret that?
You mean this integral can be positive or negative, right?
Yes, sir.
Yeah, that's true. Yeah. So that will be the case, that some agents will be compensated and some agents will be asked to pay, right? Yeah.
Okay, sir.
That will be the case. The sum of TIs will be equal to 0, but some will be asked to pay and some will be paying.
Sir, also can you please explain how did we get this first equality?
So first equality comes from the revenue equivalence formula, which so remember, this is the formula, right? So any Bayesian incentive compatible mechanism is like this. Okay.
Oh, okay.
Okay. So here basically, if you switch, VI prime is equal to VI star, and you use the fact that QI is the efficient rule, so QI VI is equal to G of VI, then you will exactly get that.
Okay, sir.
Okay. Okay, so once you have this, then the result is immediate. It requires basically some algebraic manipulation, but basically the main idea is we have computed the ex ante value. So basically here this one is an interim transfer value, right? So TI-VI is this interim transfer that agent I with type VI is expecting to get. And we have shown that it is lower bounded by this particular term. But if you integrate it one more time, then you will get this particular term here, right? So expected transfer of agent I would be, you integrate this also with respect to VI, okay, is greater than equal to this, right? And basically then you can use this because the sum of these expected payments is equal to 0. So that means that 0 will be greater than equal to the sum of expected term of this particular amount. That's exactly what I have done here. So it's a lot of algebraic manipulation. So we know that 0 is equal to this. That's this one. Okay.
Sir, in this slide, where is V minus I in the above expression?
Which one? Here.
Yes, sir.
So there is no V minus I. So this is an interim expectation, right? So this is my interim payment. Okay. And basically this is my expected interim, so I'm taking another expectations over this interim payment. So that will give me the ex ante payment. That is, before I realize my type, what is my expected payment from this mechanism? And I'm summing over all the agents.
Okay, sir.
This is just another way of writing the same thing. If you expand this TI, VI, you will get basically, it's just another way. We have done this earlier, so it's just the same thing, whether I compute it this way or basically take every valuation profile and compute the sum of payments of everyone and then take the expectation, it's the same. And because it's budget balance, it will be equal to 0.
Okay, sir. Good.
Okay, so what I have done here is nothing. 0 equal to this, we already know from this. And then basically this bound is what we have got here. TI-VI is greater than equal to this. So once I have this, I just substitute TI-VI by this bound. Okay, and that's it. So rest of the this thing is just algebraically manipulating this. Okay, so what I have done is basically split this inner integral into 0 to V star I, then subtracted 0 to Vi first. Okay, the advantage of that is that this particular term is independent of this outer integral. So I basically take this out and just integrate this from 0 to beta f of Vi. But this is a distribution, so this integral is just 1, right? F of Vi 0 to beta dvi is just equal to 1. So this basically becomes this, the first one. This one, I change the order of integration and it simplifies. So this is exactly like Myerson. We just flip the order of integration and we'll get a term like this. Okay, so the two integrals become one, and because this basically becomes an integral from 0 to x f of x, or x to 1 f of x. Okay, so as I said, so once you get this, a little bit of here and there shifting around these terms, you'll get exactly what you need. Okay, so I don't expect you to follow this on this slide, but if you go back and look at my notes or the slides, it'll be pretty clear that it's just maneuvering of terms here and there, and you get what you want. So the crucial thing to understand is how do we get this inequality, and I have explained how we get this inequality. Once we get this inequality, it's a matter of integrating both sides of this inequality and using this. That's all. Okay. So it's a necessary condition, and the question is this condition also sufficient? Right. So that's what we're going to do next. So for sufficiency, what we will have to assume is that we have a mechanism which, we don't have a mechanism. We have a partnership which satisfies this inequality. Okay, so there is a partnership which satisfies this inequality, and we have to show that this partnership can be dissolved efficiently, which means that we have to construct a mechanism which is efficient, budget balance, BIC, and interim IR. So the proof has to be constructive. So we will construct a mechanism and show that it will satisfy all the constraints if this inequality is satisfied. That's the sufficiency direction. Okay, so we assume that the inequality holds for a partnership R, so that the inequality that is stated in the theorem, and then basically we are going to construct a mechanism. Okay, so to construct a mechanism, what I have done here is the following. So right, so remember this inequality is uses v star I and v star I in this integral. So instead of I have defined a new function which I call wvi. Okay, so this is a new function that I'm defining, so that I can use it inside to define a mechanism. So this wvi is the same expression that we have in the inequality. It's the same expression, except that instead of v star I use any arbitrary vi. Okay, so essentially the inequality is sum of v star I is greater than equal to 0. If you substitute vi equal to v star I, then we exactly get this term inside, and the inequality is sum of v star I is greater than equal to 0. Okay, so let's keep this in mind. Okay, and using this, I'm going to define what I call another term, which is CI. So CI would be like an you can think of it before entering the mechanism. The CI is the amount that the designer will give to everyone. Okay, so it's just like a the CI term will be positive for some people and negative for some people, and it's basically as you will see that before entering the mechanism, the designer will give this CI amount to each agent I, and that will be a subsidy to some people and collect some payments to from some people. Okay, but the important thing is the CI is constructed in a manner so that sum of CI is equal to 0. So some people will be subsidized and some people will be asked to make payments. And by construction, the sum of CI is equal to 0. So if you sum this thing will become sum of WV star I, and this thing will also become sum of WV star I. Okay, so it will become equal to 0. So is that clear how the sum of CI is equal to 0? So at this point, I've just defined this CIs, which will be distributed before the start of the mechanism, and now we can define the mechanism. So obviously, the allocation rule has to be efficient, right? Because we want to dissolve this partnership efficiently. So the allocation rule is efficient. So we
Sir, is there any deeper interpretation of CI?
Not at this point. So it's very difficult to interpret what exactly the CI is, what is this W function, and so on. So at this point, it is constructed in a clever manner so that the transfers are balanced and interim IR is maintained. That's all. Okay. So it's just a clever construction. That's it. So the transfers, as I said, there is a CI term. So this is the term which is independent of anybody's type. So it will be given irrespective of what happens in the mechanism. But then there are terms which are dependent on this small g, the density of this capital G distribution. Okay, and again, there is no real intuition about what these terms mean and so on. The only thing to observe here is they are cleverly constructed so that when you sum over all TIV, it will become sum over CI, and this sum will exactly become this sum. It's done in a clever manner so that this sum is equal to this sum, so they will cancel each other out. Okay. And because sum of CI is also equal to 0, so what we have is that sum of TIV is equal to 0. So the transfer function is constructed so that budget balance is maintained. Okay, so far we have satisfied two properties. The mechanism is efficient because the allocation rule is efficient. The transfers are constructed so that the sum of payments is equal to 0. So what remains to be shown is two more properties, that it is defining transfer like this will be Bayesian incentive compatible, make the mechanism Bayesian incentive compatible. And the second is interim individual rationality is satisfied. Okay.
In the right hand side, we will get n by n minus 1 summation j not equal to I.
Not n by n minus 1. So remember, this is j not equal to I. So you will get n minus 1.
So
Right?
it is dependent on I.
Yeah, j is not equal to I. So this summation is over all the other agents. So it's basically, it's you have this i's term here and the average of all the other agents term here. And i's term is like a negative term, and the average of others is basically a positive term. So when you sum across everything, everything will cancel out.
Okay, sir, got it.
Okay. Okay, so to show that these interim individual rationality and Bayesian incentive compatibility holds, we will have to use our earlier results. So remember, interim individual rationality is to show that the interim payment of V star I is greater than equal to 0. So that's what we have to show. And for Bayesian incentive compatibility, we have to show this. We already know that the allocation rule is efficient. So the first part is automatically satisfied. So what we need to show is that this part is satisfied. Okay. So that's what we will show. These two things that we will show. And so for that, first step is to compute the interim payments. And again, I'm not going to go through this algebraic manipulation. What this is saying is that this payment function is constructed cleverly so that when you integrate out V minus I, okay, from this, okay, so obviously this doesn't depend, the first two terms doesn't depend on V minus I, but this one does depend on V minus I. And when you integrate that out, okay, so when you integrate that V minus I out, what you will get is Ci plus WVI. That's what you will get. Okay. So feel free to go through this, carefully and see if you understand it. If you don't, then I'll be happy to answer this. It's nothing exceptional. I mean, it's just cleverly integrating it and changing the order of integration and so on. Okay, but the point is that interim payment of any type VI is equal to this CI. So CI, remember, is this term which is independent of VI plus WVI. Okay, so this was by design. The payments are designed such that the interim payment depended on this W function. Okay, so CI plus WVI is the interim payment. Now we know that for IIR, we just need to ensure that this is greater than equal to 0 for V star I. So we need to ensure that CI plus WV star I is greater than 0. But if we substitute what CI was, so CI is defined to be this. So CI plus WV star I is exactly the average of WV stars. Okay. But remember, the condition inequality is that this total WV star I is greater than equal to 0. So the average is also greater than equal to 0. So what we will get is that the Ci plus WV star I is equal to this, which is greater than equal to 0. So this
Sir,
is
till now we have not shown that TI-VI is of the form which satisfies the Bayesian incentive.
no, we haven't shown that. We haven't shown that. So we haven't shown Bayesian incentive compatibility yet. I showed you interim IR first. Yeah, you're right. So Bayesian incentive compatibility is on the next slide, and it follows pretty straightforwardly, because all I need to show that TIVI minus TIV star I satisfies that formula, and by our construction TIVI is this. So TIVI minus TIV star I is this, and this by construction, if you look at the WVI formula, it will just boil down to this, and this basically expands to this. Okay, so that's what it is. Okay, so it just follows from our construction here that it is Bayesian incentive compatible. Okay, so this mechanism is Bayesian incentive compatible. It's not dominant strategy incentive compatible, because this revenue equivalence formula that we are showing is satisfied is on the interim terms. So it is Bayesian incentive compatible, not dominant strategy. It's not a Groves mechanism. Okay. So the only place where we use the inequality is to show that interim individual rationality is satisfied. So what this is saying is that this mechanism is efficient, budget balanced, and Bayesian incentive compatible. It satisfies three properties, even if the inequality is not satisfied. Okay. So for an arbitrary partnership structure or share vector, the constructed mechanism satisfies efficiency, Bayesian incentive compatibility, and budget balance. Okay. But it may fail interim individual rationality. But if the inequality is satisfied by the property right structure, then even the interim individual rationality is satisfied. That's where we are using that inequality. Okay. Nowhere else I had to use the inequality. Only at this place I had to use the inequality. This is something that you should keep in mind. Okay, so that's basically the proof. So what we observe is that the proof is basically the construction of the mechanism. There is a mechanism, but the mechanism is quite mechanical. So there is no interpretation of this. But that's okay. So it's a theoretical result which shows that it is possible to design a mechanism which satisfies these four properties if and only if this CGK inequality holds. So let's call this inequality CGK inequality, Crampton, Gibbons, Klepper inequality. So if and only if the CGK inequality is satisfied by the partnership, then we can construct this efficient BIC, IIR, and budget balanced mechanism. So full surplus redistribution is possible. Let me give some comments about the proof. One thing that you must note is that the proof works out even if we replace budget balance by the fact that sum of payments has to be less than or equal to 0. So, of course, the sufficiency direction is not a problem because the mechanism that we construct is already budget balanced. But in the necessary direction, even if you have that sum of TIV is less than equal to 0, okay, then also the proof will work out, because then this thing will become less than equal to 0, and here you will have 0 greater than equal to this, and everything will still work out. Okay, so the proof works out even if we replace budget balance by what I call feasibility, that is the sum of payments is less than or equal to 0. The mechanism proposed in the proof is quite complicated. So we don't expect such mechanisms to be used in practice. So if you look at the paper, for this particular reason, they propose simpler mechanisms which can dissolve every dissolvable partnership. So basically, there might be many partnerships which satisfies these inequalities. amongst that, for some of those partnerships, a simpler mechanism may work. And what is an example of a simpler mechanism? Here is one example. Every agent bids, okay, for the object. Highest bidder is given the entire object. So that's achieving efficiency in some sense. Okay, so highest bidder wins, and highest bidder pays her bid, and then her bid is equally divided between all the agents. So of course, this is an indirect mechanism. So a Bayes-Nash equilibrium of this mechanism will have agents bidding lower than their value. So in the Bayes-Nash equilibrium of this game, agents will underbid. But even if they underbid, the the equilibrium will be symmetric. So actually the highest valued bidder would also bid the highest. So it will be efficient. Okay, so and by construction, the mechanism is budget balanced because highest bidder pays her bid and her bid is equally distributed, divided between all. It will satisfy. So the trick is to show that it will satisfy interim individual rationality, and basically that is shown by the shown that for a large class of partnerships, it can still satisfy the equilibrium of this game will satisfy interim individual rationality. Okay. I'll pause here. Is there any question on this part so far?
Sir, at first we took feasibility to be QI, the sum of QI should be less than
Yeah.
1.
So I should change the terminology of this section. So here I'm using feasibility in two ways. So earlier I had defined feasibility to be like sum of QIV less than equal to 1 and sum of TIV equal to 0. At many places in the notes, I have used feasibility to be just sum of TIV less than equal to 0. So it's kind of contradicting. So let's call this to be feasible in this model, and this I will call it payment feasibility. Okay, so I'll call this something else. So this to be payment feasibility. Okay. So payment feasibility just means that sum of TIV is less than equal to 0.
Okay, sir.
Any other questions? Okay. So as I said, I mean it's a complete characterization of what partnerships can be dissolved. So what will be more interesting is to look at the corollaries of this result. So how can we apply this result to say like what kind of partnerships we can completely redistribute the surplus essentially, okay, efficiently dissolve. So here is the first one. Here is the first interesting corollary. The corollary is that one seller, many buyer partnerships cannot be dissolved efficiently. Okay, so if you have a partnership where let's say one of agent one has the entire share and everybody else has zero share. So agent one is like the seller in this case, and everybody else is the buyer. So if we have such a partnership, then we can never dissolve it. Okay. So one basically interesting uh, 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 what do you say? The special case of this is the bilateral trading model, where there are just two agents, one
Sir,
seller.
your voice got interrupted. Can you repeat it again?
Oh, sorry. Uh, so I was going to derive the corollary, one corollary of this. So the corollary says that one seller, many buyer partnerships cannot be dissolved efficiently. So what's a one seller, many buyer partnership? So these are partnerships where there is exactly one agent who has the entire share and everybody else has zero share. So you should look at those agents who have zero share as buyers, and the agent who has the entire share is the seller. Okay, so the result says that such partnerships cannot be dissolved efficiently. A special case of this is the two agent problem where R1 equal to 1 and R2 equal to 0. So those are bilateral trading problems, okay, where there is one buyer and one seller. So the result, basically another way to read this in the two agent case is that in the bilateral trading problem, there is no mechanism which is efficient, budget balance, interim individually rational, and Bayesian incentive.
Excuse me, sir.
Yeah.
In this case, efficiency and IIR will try to contradict each other. Is it correct?
Not really. Why?
Because efficiency will demand the highest valuation buyer to get the object.
Yes.
But then his value, if it is less than the value of seller, then the seller will get something which is less than his reserve value.
So he needs to be compensated enough, right? So basically, so let's look at the bilateral trading model where there is a buyer, let's call him B, and there is another agent seller who is S. So efficiency will say that trade only occurs if VB is greater than VS, right?
Yes, sir.
If the value of the buyer is greater than the seller's, then the seller should sell the object to the buyer. Okay, because VB is greater than VS, to maintain individual rationality, okay, I'm talking about expose now, but to maintain individual rationality, basically the buyer has to compensate the seller enough. So he has to pay him at least VS, right? That's what it is. But he can do that because VB is greater than VS. Okay, so efficiency and individual rationality is not really incompatible. It is only in the presence of Bayesian incentive compatibility and budget balance that we get contradictions. Okay. So, so what we will show is that so this bilateral trading version of this theorem is also known as the Myerson-Satterthwaite impossibility result. It was proved earlier than this paper, but only proved for two agents case. So that's why it's called the bilateral trading problem. But a corollary of this result is that theorem also extends to the n agent case, where there is one seller and many buyers. Okay. And what we'll show is that essentially, to prove that theorem, what we have to show is that if the partnership is like that, R1 equal to 1 and R2 to Rn is equal to 0, then this inequality can never be satisfied. Okay. So that will mean that it cannot be dissolved efficiently. Okay. So we'll show that this inequality, this expression is always less than 0. Okay. For such partnerships. That's what we need to show.
Sir,
Yeah.
sir, every DSIC mechanism is also BIC. Right?
No, DSIC mechanisms are stronger, right? I mean, dominant strategy is a stronger requirement.
Okay, yeah, got it.
Yeah. So, I'm sorry, what did you ask? Every DSIC mechanism is also?
Bayesian incentive. That
Yes,
would be correct, I think.
yes, that is correct. Absolutely, yeah. Yeah.
So why don't we just use the victory option or something like that in this case?
So victory auction will not be budget balanced, right? So
Why not? One is paying and one is getting. So what is transferred is it's balanced.
so, but then you have to remember that if you do a victory auction only amongst the buyers, that will not be efficient, right? Because there is also a seller's value in this model.
Yeah, that is right. So there is a reserve, and if the value is greater than the reserve price, the object is sold. Otherwise, it is not, and it goes to the highest valued buyer.
Okay.
So I don't see a problem with that.
Right, but then how does you have to consider the seller also, who is strategic about his value, right? So basically, so notice the following. So So in some sense, what you're saying is everybody announces their values. Okay, right? I mean, if I want to do a victory auction with all the N agents, right? So what should I do? I should ask everyone to announce their value. The highest
Yeah.
bidder gets the object. So that might be the seller itself. Okay.
Yes.
And he pays the amount of the second highest bidder.
He doesn't pay, right? He pays. He has to pay to himself. So he doesn't pay.
What do you mean he doesn't pay? Then it will not be incentive compatible. Then he can manipulate, right? If he does not have to pay, okay, so it will not, so he can manipulate. So I think this is a good exercise to think that if you do, when the seller also has a private information, that is, he can lie about his value, then if you do a victory auction, the seller would not report his true value.
Suppose seller's value is 10 and there are two buyers whose value is 20 and 30.
Yeah.
So buyer 2 wins and he pays buyer 1's value
Yeah.
in victory auction, but then
Yeah.
seller receives nothing.
Yes.
As the owner of the object in first place, so that contradicts IIR.
No,
No, I'm saying the seller receives the payment.
the seller receives the payment, right? So in that example, let's look at this example that Manoj proposed. So basically, seller's value is 10 and there are two bidders who have 20 and 30. Okay, right, value. So in this case, what is your mechanism? What is the payment of this mechanism? So the 30 buyer wins and pays 20 to the seller. Now this,
Okay, so he can manipulate. He can get better payment.
yeah, so he will just announce his value to be 25.
Yeah. Okay.
Okay, so basically that's why I had proposed all these green Laffer mechanisms, where if you want to do a victory, basically you have to do this residual. I mean, you have to take out an agent whose type does not matter and so on, and that basically creates inefficiency. Okay, we'll come back to such mechanisms in the next lecture. Okay, so anything with
Also, sir.
dominant strategy will not work.
Okay, and the Myerson's case, which we had discussed, that doesn't work because the allocation is not.
Not only that, so basically in the Myerson world also, the seller has no type. The seller is the mechanism designer. So here the seller is also a participant in the mechanism. So so the seller is also strategic in that sense. In the Myerson's world, the seller is just is the designer himself. So he is not someone who is posting fake reserve prices and trying to manipulate the mechanism and so on and so forth. Right. So here the difference is the seller is a participant in the mechanism. Okay.
So this whole idea is basically a generalization in the sense that there can be more than one owners of the object which have strategic interaction in the model.
Exactly. So I think the best way to look at this Crampton-Gibbons-Klemperer model is there is no mechanism designer. So there are a bunch of agents who have got together. They have got an object with themselves, and they each, legally there is some contract which they have signed, which allows them to claim certain portion of the object. Now they want to dissolve that partnership, and they have to dissolve it between themselves. So there is no third party which can come and put money into the system or take away money. If they conduct a victory auction between them, so it will generate some money and somebody can take it away. So those kind of things are not allowed in this model. So essentially the tension is you have to have this budget balance. So basically it's an exchange of money between them. You have to do it efficiently. You have to do it budget balance. You have to maintain incentive and participation. demonstrate. Is it possible? So what this corollary is saying that if your partnership structure is so asymmetric, I mean completely asymmetric, that one guy has all the shares and everybody else has 0 shares, then you can never do it. Okay, that's what this is saying. Asymmetric partnerships are pretty bad. Okay, so the proof is basically showing that that inequality cannot be satisfied. And the main observation here is that if one of the guys is RS is equal to 1 and RI equal to 0, remember what V star I was. V star I is the point where G of V star I is equal to RI. But if Ri equal to 0, then those V star i's is equal to 0. Because G of 0 is equal to 0. Okay, and if Rs equal to 1, then V star S has to be equal to the upper bound of the distribution, which is beta. Okay, so V star S is equal to beta and everything else is 0. So this inequality, remember, is the inequality was the sum of W V star I. That's the summation. So we have to show that this is strictly less than 0. But this simplifies to W of beta plus n minus 1 W of 0. And then basically you expand those W expressions and do some algebraic manipulation, and eventually you get a term like this, and you see that this is clearly strictly less than 0. Okay, so these algebraic manipulations, I'm not going through them, but you can verify. Just involve some integration by parts and to simplify things, but you can do it, and basically you get to a term like this, and this is always less than 0 because fx is strictly less than 0, so less than equal to 0.
Sir, how much we can relax the conditions to get a possibility here?
This one?
Yes, sir.
You mean what other RIs continue to give you impossibility?
No. In this case, when R1 is equal to 1 and others are 0, what conditions need to be like relaxed so that we get a possibility here?
Well, we have to relax one of the 4 constraints, right? So we have BIC, efficiency, interim individual rationality, and efficiency. So we have to relax one of these 4 conditions. Okay, we'll talk about them. So we will talk about relaxing these conditions.
Okay, sir.
So right, so this is the impossibility result. Here is a possibility result. The possibility result says that symmetric partnerships can always be dissolved efficiently. Right, so symmetric means all the Ri is equal to 1 by n. Okay, so what it means is that if you have let me go back. So equal partnerships are partnerships where each agent has equal share of the firm of the object. In that case, what we can show is that this inequality is always satisfied. Okay, irrespective of what that capital F distribution is, okay, this can always be satisfied. For the completely asymmetric case, which is the one seller many bar model, we showed that whatever F is, this inequality cannot be satisfied. Here we are proving the other part of the result, which is that if you have equal partnership, this is always satisfied. Okay. In fact, the result is slightly stronger than that. It says that the set of partnerships that can be dissolved efficiently, that is the set of partnerships which satisfy that necessary and sufficient condition, is a convex subset around the equal partnership. So it's not only the equal partnership, but some convex set around that equal partnership which can always be dissolved, independent of what capital F is. Okay, the distribution is. Okay.
Suppose Ri is equal to Rj for all I and j, and Ri is equal to Ri is strictly less than 1 by n. So does this result hold in that case?
No, but if all the agents have same share, then it's equal to 1 over n.
Cannot we take it like less than 1 by n? There is some share which is for some outside party, which is not a strategic agent in this case.
So in that case, basically you can scale everything down. So basically, so in that case, basically that amount of the object is not owned by anyone, right?
Yes, sir.
So basically in that case, what you can do is you can allocate whatever people own efficiently, okay, and give the a quantity that is not owned by anyone to the agent who has one, basically for free. Okay, so I think it's a matter of scaling things and so on. It's not going to be problematic.
Okay, sir.
So as I said, this sum of RIs is equal to 1 is only for convenience. You can always have it less than 1 also, and it's just a matter of scaling things. Okay.
Okay, sir.
Or another way to think about it is if some portion of the object is not given to anyone, you can basically uh, first distribute that portion equally amongst all the agents and define a new RI and then dissolve it efficiently. Okay, so that way also. Okay, so the picture here is a picture which I had drawn for 3 agents. So this is the simplex of partnerships. So basically there are the diagram is only for 3 agents. So the extreme points are the points where one of the agents has the entire share and the others have 0. Okay, and what is it called? The centroid of this simplex is basically the 1/3, 1/3, 1/3 point. Okay, so so essentially, if you are on one of these edges, then one of the agents has 0 share, and the other 2 agents are sharing the object. Okay, so that's that partnership. So here I have drawn for uniform distribution. If capital F is uniform between 0 and 1, okay, then what is the set of partnerships that satisfy this CGK sufficient condition? Okay, so necessary and sufficient condition. And as you can see that the set of partnership that satisfy that condition is a convex subset around this equal partnership. So it contains the equal partnership. It also contains many other things. But notice that it never contains the extreme partnerships. This 1, 0, 0, 0, 1, 0, 0, 0, 1 are never covered. Okay. So if you take some other distribution, let's say not uniform, but something else, the picture will be again a convex set, symmetric convex set around the equal partnership, but it may look slightly bigger than this or smaller than this, depending on what your capital F is. Okay, but the important thing is that the extreme ones will never be touched. Okay, and the equal partnership will always be there. Okay, that's what this result is showing. Any
Sir,
question?
are the scales marked incorrectly over here?
Players? No, I haven't marked.
Scale.
No scale. Yeah, scale is marked incorrectly. Unfortunately, I think. Yeah, the scale is marked incorrectly. So
Also, the equal partnership is it at the center of this convex subset?
yeah, it will be at the center of this convex. So 1/3, 1/3 will be somewhere here, and that's not that's where it.
Okay.
Can you repeat what you just said? My connection got interrupted.
Yeah, I'm saying that the scales marked here are kind of not exactly correct, I think, or maybe they are correct. Now thinking.
It's not. Right? So the bottom axis one should come at the rightmost point.
Well, not really, because remember we are so. So remember, the way to measure this would be like, so if you take a point anywhere here, anywhere in this triangle, its coordinates are the lengths of the perpendiculars to each of the sides. That's how you have the simplex coordinates, right? So you take a point here, and the perpendiculars are basically the length of uh, uh, the length of the things x, y, z, right? So I think in that sense this might be correct, because here this point, okay, is basically going to be 1 0 0, right? So that means that this perpendicular should be of length 1. So that's what it is marking. Okay, so this is 1. Okay, so it is in the correct scale. Okay, so this perpendicular is 1, and the perpendicular to the other two sides is obviously 0. Okay, so it is in the right scale. Okay, so
Look at this point in the horizontal axis.
yeah, so this point, okay, so for instance this
That should be 1.
no, not really, right? What should be 1 is the length of this perpendicular should be of length 1. Okay, so this should be like what um, uh,
If only these two people are sharing the bottom two vertices, then the total should be 1, right?
the total should be 1, but it should not be marked as 1.
Root 3. Root 3.
It should be square root 3 or something like that, I think. Yeah, I think it's square root 3, which is what it is. Right? So I'm sure in proving von Neumann-Morgenstern expected utility theorem, you made use of simplices, right? Didn't you? So basically
Yes, sir.
so the way, it's a two-dimensional diagram to represent a three-dimensional object, right? So R1, R2, R3 is represented in a two-dimensional picture because R1 plus R2 plus R3 is equal to 1. Okay, so the good thing of an equilateral triangle is that if you take any point inside it, the sum of perpendiculars is always the same. Okay, and here I have taken it such that if you take the sides to be square root 3, then you will get that.
So that should be root 4 by 3 then.
Which one?
The length of this line on the horizontal axis should be root 4 by 3.
Root 4 by 3.
The 2 by root 3. Exactly 2 by root 3.
Yeah, that's what I said. Root 4 by 3.
Yeah, something like that. Yeah, probably 2 by root 3. Yeah, you're right. I think. Yeah, something
2
like
by
that. But the point is, it should not be 1. Okay,
That's
let's not discuss this further. It's clear that it should not be 1. So whatever it is, but the point here is that the set of partnership that can be dissolved is around the equal partnership of convex set. So here I have drawn for uniform, but you can draw it for any arbitrary distribution. Okay, so how do you prove this? Well, the proof basically shows that inequality is always satisfied for equal partnership. Okay, so I'm not going to discuss the convexity proof. You should look in the notes how it is done. But for the what I will discuss is the proof that equal partnerships can always be dissolved. Why is that? Well, for equal partnership, everybody has the same V star I because everybody has the same Ri. Okay, so basically V star I is the point where G of V star I is equal to 1 by n. So I'm going to call that V star. Okay, so remember the condition was sum of W V star I is greater than equal to 0. Well, if everybody has the same V star I, that condition is equivalent to showing that W V star is greater than equal to 0. because everybody has the same V star. So we need to show that W of V star is greater than equal to 0. And basically that follows, you just write down the expression for W like this. You should go back and check what is the expression for WBI. This is the expression for, BI. If you write it down carefully, it'll look something like this, and you substitute for G of X and expand it, do some integration by parts, both the things you integrate by parts, and you'll get some expressions, and eventually you'll get an expression like this. Okay, so once you get an expression like this part is always non-negative. So, and this part has this term in common. So if you can show that beta minus V star is greater than equal to this, then you're done. Okay, so basically that's what I show here. I show that this expression inside this integral is always less than equal to 1. If it is less than equal to 1, then basically this integral is only this integral, okay, is going to be less than equal to beta minus V star, and that's what, so the whole deal is to show that this is, less than equal to 1, and that you can basically, cleverly show that this expression is basically increasing from V star to beta, and basically at beta this is the maximum value is 1, and so hence this is always less than equal. Okay, so that's what I showed. So once you have this, then you prove that V star is. So as I said, these corollaries are very straightforward application of that inequality. Once you have that inequality, you take these particular partnerships and you manipulate that inequality and show whether it satisfies or not. Okay, so there is no extra work that you need to do. Just simple brute force calculation will give you one way or the other. So for the extreme partnerships, we showed that they can never be dissolved efficiently. For the equal one, we show that that inequality is always satisfied. Okay, so let me make some quick comments. So this CGK result is remarkable because it clearly spells out what is possible and what is not when dissolving a partnership efficiently. So it says that in a very, very symmetric informational environment, what kind of partnerships can be dissolved efficiently and what can be not dissolved. It's a matter of verifying that single inequality. Okay. This symmetry of agents is crucial in the sense that, you remember, we took that each agent is drawing its value independently and identically. So both these assumptions are crucial in the whole analysis, that all the agents are drawing from the same distribution with the same support and their values are independently drawn. Okay, so so these things are crucial, and there is a paper, if you want to look at it, if the independence is there but the value distributions are not symmetric, then the results of Rampton, Gibbon, Klepper does not really go through. Okay, so so the equal partnerships may not be dissolved and so on and so forth. Okay, so that's what this paper does. There are other papers which I cite. I mean, if you want to look at it, these are for people who are interested in knowing more about this model. So one paper that I must strongly recommend is this paper, 2019 paper, so which basically says that, suppose I'm a designer and I can design the partnership structure. Okay, so the distributions may be symmetric, may not be symmetric. If I know that the distributions are symmetric, or that is everybody is drawing from independent and identical distributions, then if I'm interested in maximizing the payoffs of the agents, then I should just design it the partnership structure equal partnership, because then I can always dissolve. But if the distribution is not symmetric, then it's not clear what is the optimal partnership structure which will maximize the sum of payoffs of the agents. Okay, so this is the kind of question that these authors have asked, and it's a good optimization exercise after the Crampton-Gibbons-Glenford. So
in the sufficiency part, we find out the optimal mechanism earlier.
well, in the sufficiency part, we gave one mechanism which will dissolve every dissolvable partnership. That is, anything which satisfies that inequality can be dissolved. Right?
But that need not be unique.
No, that mechanism need not be unique. There are many mechanisms which can work, but they just propose one. Okay, for so let's say the equal partnership, the equal partnership can be dissolved by this mechanism. Also, everyone bets, highest bidder wins, highest bidder pays her bet, then that bid is equally divided between everyone. This mechanism will dissolve the equal partnership. Okay, so the Bayes-Nash equilibrium of this game, okay, would be something which will be efficient. Of course, the mechanism itself is budget balance. It will also satisfy interim individual rational. So in the equal partnership case, it will give every agent 1 over n of its value.
So will this mechanism be identical to the mechanism which we get if we use the sufficiency part?
No. So that's the point. So this is a much simpler mechanism. That's a much complicated mechanism. It won't be the same mechanism. So the mechanism proposed in the proof may be redistributing the surplus in a different way, still redistributing the entire surplus, maximum PI, but in a different way, and this might be redistributing in another way. Yeah.
Okay, sir.
Right. So that basically says that there might be different mechanisms which can do the job. Okay, so let me stop this. In the next class, we'll try to relax some of the constraints here and see what happens with that. Any questions?
Have you decided about the exams?
Yeah, I mean, let's wait. I'm still thinking how we will do it and so on. It won't be a physical exam where you will be required to come to ISI, but it will be something else. I'll let you know. Okay, and the timeline is basically, next class will be the last class in terms of lecture. Then I'll have one more class where I will like to clarify any doubts you have, and basically, so that will also happen next week, and then we'll discuss about the exam and come up with something. Okay, so I'll strongly suggest that you keep reading the notes, and I had sent the latest version last time in the email, and also the lectures, and collect your doubts. Okay, and also conceptual doubts like so for instance, some of you might be wondering, why is this mechanism not working all the time? Why is this mechanism only working for 1 over n and not for everything? So some of you might be thinking, why is it that this mechanism has a truth-telling equilibrium? Why is it not a dominant strategy mechanism, right? So all these things, you know, however stupid it looks, please think about things and you know, try to get a sense of all these lectures. So as you saw that after the matching lectures, we have been going on single track, right? So it's only about single object allocation problems, but understanding this single object allocation in a lot of detail. Okay, and so if you have a good sense of what is happening here, then you will be able to understand more advanced things and also apply these things in many problems. Okay, any questions? Okay, then okay, then see you next week. Okay.
Okay, sir.
Okay, bye.
Bye.